Thanks everyone for continuing on. This is the last talk. And as the last talk, you might think it's time for a step back and look at the field in broad cases like what Paul did, but no, that's not me. We're going to go deep and we're going to go into Soar and ACT-R. So let's start with a common model of cognition. The idea of it was to provide an abstract specification of the human level cognitive architecture. It was supposed to be a community consensus and not itself a cognitive architecture, but still have many of the components. And as you can see on the side, the basic idea is a set of communicating modules, and it's just not undifferentiated stuff. It's just not a bunch of neurons. There's actual structure here in terms of what's done in the individual modules and how they interact. And they're not task-specific modules. They're more general than that. So you don't find a riding your bicycle module, or even a planning module, or a natural language module. So the potential benefits is that we hope that that provides a baseline to facilitate communication among the community, so that we have a set of common terminology we can use when we talk about architectures. And maybe it can provide guidance in where there's things that are unknown that we have to do more research on, and possibly also a testable theory about the different structures. And one of the shocking results of this has been that this structure that we have up here in the corner has been tested on human data by Andrea Socco and his collaborators, and found to be one of the best, or even the best, explanation for how things move throughout the brain during certain kinds of tasks. And it's very important that we are not saying this is a prescription for how cognitive architectures should be defined. This is more a looking at cognitive architectures and finding what's common. And that's what's going to be true in my talk as well. Don't say this as we're saying, if your cognitive architecture doesn't work this way, it's a mistake. No, different cognitive architectures have different purposes, and they might have very different structures. So what is some of the structure and processing in the cognitive model? Well, the processing is a central cycle that's about 50 milliseconds, and that's through retrievals from procedural memory. There's parallelism in all the different parts in terms of when they're making their own processing. And complex behavior arises not because of special purpose modules, but because of extended processing throughout the cycles of these different simple modules. And we have certain theories about learning, that all knowledge is learnable, and that the learning mechanisms are associated with the long-term memory. That's kind of obvious. But a key point is the architecture structure itself is not open to learning. The architecture learns and interprets knowledge that is the contents of these memories, but the knowledge itself cannot access architectural internals. So the talk goal is to look at these two architectures which look very different, Soar and ACT-R, and try to dive deeper into their functionality and really say, what do they have in common beyond what we've talked about in the common model? Also, how do they differ? Can we formalize their processing a bit? And this is definitely a bottom-up approach. Me reading manuals in ACT-R and Soar and talking to people and saying, how does this actually work? And all the mistakes I'm going to make in terms of talking about ACT-R are mine and not the ACT-R folks. So we will continue to iterate with them until I get it right. I am completely ignoring how these things map onto cognitive modeling or neural structures, and I'm ignoring anything to do with software implementation issues and things like that. Spoiler alert, there's going to be more in common here than you might think, or at least there was, than what I thought. So the talk outline is we're going to go through, we're just going to do it. We're going to talk about agent data and agent metadata, which is different than what Paul has. We're going to talk about working memory. We're going to talk about procedural memory. We're talking about declarative memory. I'm going to skip perception, sorry, John, and motor just because I don't have enough time. And we're not going to talk anything about decay and forgetting. This is going to be a slog. So have that second cup of coffee or latte or whatever. And I am not going to slow down. So it's just going to keep going at about 0.8 newels from here on out. All right, so let's go on to the next slide. Let's define what I mean by agent data. The agent data is what is the contents of these memories. So it's the contents of working memory, the contents of procedural memory, and declarative memory. Each of those consists of memory elements. And so actually a big thing is that memory can be decomposed into independent elements. And that's what encodes all the agent task knowledge. Elements can be created and modified and deleted and tested independently. Sometimes elements are combined together into chunks, but in general, they can be but they can be treated independently. And the architecture, this is a really key point that's kind of subtle, is the architecture only understands the form of the knowledge. It doesn't really understand the contents. It doesn't understand what's in a rule, but it knows how to match a rule against working memory. But it doesn't know what's going on in terms of those underlying representations. There's a few exceptions in that the connections between the modules, like when I send a command to the motor system, or I send a retrieval command to declarative memory, there are some forms of specificity that the architecture understands so it can initiate those interactions, but that's about it. What about metadata? This is where I diverge from Paul. I take a very classic definition of metadata, which is data about agent data elements. So metadata is data about working memory elements, or about declarative memory elements, or about procedural memory elements. It's sometimes numeric, and sometimes people call it subsymbolic, which it shouldn't be called, I don't think. Subsymbolic could be how you implement these elements in another technology like neurons, but I'm talking about additional data that's associated with these things. Imagine that you are a Soar architecture person, and I say, I want to capture the state of Soar after we've gone for 14 decisions. What do I have to write out to a file so that when I read it back in, it's exactly at the same state? Well, that's clearly all the agent data, and it is also the data about that data that the architecture uses to interpret it and make decisions. And so that's what I think of in terms of metadata. And it's a lot more than I think you often think, and it's not always numeric. So activation of long-term memory elements is the classic metadata that's used in ACT-R. Utility of procedural memory elements is another classic view of metadata, but there's also going to be relational metadata. All right, so metadata is created and tested by the architecture, and it's not, as we have formulated it in Soar and ACT-R, it seems like it's not accessible to agent data. You can't test what the activation of a declarative memory element is in working at any time. Also, you can't change it. The only way you can influence it is indirectly through rehearsal. And you can maybe get an idea of what it is by doing some activities and seeing which thing comes back from declarative memory. You can say, oh, well, that must have a high activation, but you can't get at it directly. All right, so that's sort of background. And now we're jumping in to talk about working memory. So working memory right here. Working memory in both systems are relational graph structures, where an element is a triple, such as a chunk name, a slot, it's called slot name, and then a value. And we're going to talk about each one of these as being a WME, and then the ith one says that's a specific one. So in my formalization I'm going to be developing, we're going to be able to refer to a specific working memory elements. Working memory elements also come together as chunks, declarative chunks, where they share a node. And so we're going to say that a WMC is a working memory chunk, and this is the ith one. So there's also buffers to other modules. So there's the declarative memory buffer, the procedural memory buffer. Well, there's not actually a buffer for that. There's a perception buffer, and there's a motor buffer. These are areas where you can send commands to these other modules. You can also receive chunks back, like when you do a retrieval from declarative memory. And so in my formalism, we're going to have the module name, DM, and then C for Q, R for retrieval, S for status. Whew. All the working memory elements can be tested by procedural memory. So that's one of the key things about it. They are not weapons of mass encoding. Sorry, Pat. So how do they differ for ACT-R and Soar? In ACT-R, there's a fixed number of buffers, and that's everything in working memory. Now here I show 3 buffers. In most ACT-R systems, there's a bunch more, such as the imaginal buffer, maybe a goal buffer, and so on. For some large systems, they actually have gone up to 14 different buffers to provide intermediate storage. And each of those buffers has a single chunk and does not have the substructure as I show here. So you would have this in a buffer, and this would not be there. You'd have this, and you could use this to get access to the rest of it later on, but not in working memory. Soar has unlimited in breadth and depth of the graph of working memory. That all must be rooted in a state so that we can have large states. And also we have multiple states that have relationships between them. And these substates are created at impasses that we'll talk about in a minute. All right, let's keep moving on. So what about working memory metadata? Now, surprisingly, in common, they do not both have anything like activation for working memory. However, there are symbolic relational types of metadata that are sort of, obscure. So it turns out that when you retrieve something from declarative memory, it's actually a copy of what's in declarative memory, and there is information in the background hidden from the system that makes this connection between the working memory chunk and what's in long-term declarative memory. And that connection is necessary for some of the processing that happens in these systems. There's also derivational metadata. This is, how did I create this working memory element? And that could be either from a retrieval from declarative memory or because it was created by a retrieval from procedural memory. This is what's used in order to build new procedural memory elements. So in chunking, in Soar, the procedural chunking, this is the information used for that. And conceptually, it's the same information that's used in ACT-R when they do procedural composition. All right, so there's no additional working memory metadata in ACT-R. In Soar, there is activation working memory because we have a huge working memory, and in some cases, we want to be able to forget things if they haven't been accessed for a long time. So we do keep activation associated with individual working memory elements. That's updated as the working memory elements are accessed or recreated. It's used in forgetting. We also have additional relational working memory element metadata. That is, what is the highest state that a working memory element is accessible from, and that's used in our subgoaling and chunking mechanisms. But what this shows is there's this additional information that's backstopping behind all this other data that you see in working memory. All right, let's jump into procedural memory. So this is asymmetric, and in common, there is this idea of a procedural memory element. Okay, these are rule-like elements that have conditions actions. Conditions test working memory elements, but not metadata. The actions modify working memory element. They initiate motor actions, modulate perception, initiate declarative retrievals, or make changes to working memory that then will lead to new procedural memory retrievals. A single procedural memory element is selected on each cognitive cycle. All right, so all the Soar people are there going, what is he talking about? Well, in ACT-R, we will say that a procedural memory element is an individual rule, but in Soar, a procedural memory element is what we call an operator. An operator is actually a collection of rules that propose, select, and then apply the operator. So these different parts correspond to the conditions of a rule, and these in ACT-R, and these have to do with the application of a procedural memory element. We're not going to go into the details of why we do one or the other, except to say in Soar, this provides us more flexibility in terms of that we can learn individual components of a procedural memory element as opposed to having to learn it all or none. All right, let's keep going. Now, how about metadata? Well, in common, both architectures maintain utility for the procedural memory elements. So this means for ACT-R, associated with each rule is a utility. In Soar, associated with each operator in a indirect way, we associate utility with an operator. It's actually in a rule that is used to select operators. These are computed via some kind of temporal difference learning, an RL mechanism. ACT-R has no other procedural memory metadata. In Soar, we do have activation, especially for actually these RL rules, because we can learn thousands or millions of these in some situations, and we might want to forget them if they're very rarely used. So this is used in forgetting. All right, take a breath, deep breath, and move on to our 2 stages of formalizing procedural memory retrieval. How do we do procedural memory retrieval? I want to formalize that a little bit, and it turns out to best think of it as 2 stages. There's a selection of a procedural memory element, and then there's going to be an application of that element. So in terms of procedural memory element selection, this is my formalization. Hold on, we're going to go through it. So the first part of the formalization says that we're going to search all procedural memory elements, that's what the star means, all, using all working memory elements, that's what the star means, in terms of matching. There's a matching process that goes on. We're going to find one, and that's going to be moderated or biased by the utility associated with those procedural memory elements. And that's then going to lead to us selecting a procedural memory element. But we need some additional intermediate results after we've done the selection. And that's what these 2 components are. The first one is the instantiation of all the conditions in the procedural memory element. So this is, in a rule, this would be all the working memory elements that matched at that rule. Okay, that's what this is going to be. And the actions are then, when we take that instantiation and we apply it to the actions of the rule, what are all the things we're going to change in working memory? What are those instantiations? So we go from searching working procedural memory, we find these 3 components, and that is stage 1. Nothing changes in working memory at this point. This is just gathering intermediate data. Now we go to procedural memory application. And the first thing we do is we execute the actions of the to change working memory. And that just means take those actions as they're instantiated and make changes to working memory for each of them. The next thing we do is we update the procedural memory utility metadata from reward. And that's what we're doing right here. So we're updating the utility based on the fact that we just fired this rule. And we got some reward signal. All right, so it turns out that in ACT-R, it's a little more complicated because they will actually update the utility of all rules that fired before this rule if they haven't had an update. They didn't get any reward information. So it's just a little bit more complicated in ACT-R. The final thing that happens is we set the working memory derivation metadata for all the actions. So this is where we're setting the metadata that we're going to be using in chunking and procedural composition. So what you'll notice is when we do a retrieval, we end up making changes to working memory, but we also do updates to metadata, and that's the way it is. All right. So, and have that. So it turns out that in Soar, it's a little different, and that's what I just wanted to show. There's a little bit of difference. So not only do we update those metadata, we also update the metadata associated with all the actions because we do have working memory activation, and that's where working memory activation gets updated. We also update the working memory activation for all the conditions. I'm sorry, this should say conditions here because because that's one of the ways we update activation. We also update the individual action activations for each procedural memory thing. So this is how we decide whether we're going to forget things in the future. And finally, one of the things we do in Soar is we detect if no procedural memory element is actually retrieved by that process I talked about. If nothing comes back, that's an impasse. And that leads us to do some extra processing, which in Soar means creating a substate for the different kinds of impasses. All right, so this is how things work in Soar. But it's on top of what we talked about before. So everything else was common, and this is on top of that because Soar has these additional types of metadata and impasses. All right, we also can characterize learning. This is really a simplification. We already captured RL updates above. For procedural composition, I'm just going to take a very simple view, is all that derivational information that we saved as metadata is now available for us to use in terms of building new rules. I'm not going to say when that happens, and that's just too complicated to try to get here. So now we're sort of done with procedural memory. We're going to move on to declarative memory, and this is symmetric data. What's common between the two is that they both have declarative memory chunks and declarative memory elements using the same relational structures as in working memory. Soar does make a distinction from ACT-R in that we split long-term declarative memory into semantic memory and episodic memory. I'm really not going to go into that much right now, but that changes how we learn things in episodic memory and how we do some of the retrievals. But most of what I'm going to go through applies to both of them. So what about declarative memory metadata? What's in common is both of them have activation associated with every chunk. So if there's a chunk, it's going to have activation in long-term declarative memory associated with it. They also have activation associated with the individual elements, and that is used in spreading activation during retrieval. That's about it for Soar, for ACT-R. In Soar, we also have some association strength updated when we do working memory. I'm not going to talk about this. And episodic memory has additional metadata associated with the elements in order to make it possible to recreate episodes and to go back and forth when we do retrievals. All right, so let's go to declarative memory retrievals. How do we do that? Well, it turns out it's two stages again. There's a select and apply. We're going to select the declarative memory element when a chunk is added to the declarative memory queue area. So we add a chunk here. We use that to search through declarative memory and to find a chunk, but we're also biased by a lot of metadata. These are activations of different aspects of declarative memory and working memory. And that's going to, using spreading activation and other mechanisms, end up selecting a single declarative memory chunk that is to be retrieved. Okay, so that's the intermediate results again. So now we go to the apply phase for declarative memory retrievals. In the apply phase, we add a copy of that chunk to the retrieval buffer. And it turns out in both Soar and ACT-R, it's a copy so that we can make changes to that working memory without changing declarative memory directly. We also update a bunch of different aspects of metadata. We update the working memory element we just created with the derivational information so we can do procedural learning. We also update the copy metadata I talked about before. We also create status information if we had a successful or failed retrieval from declarative memory. All right, so there are some differences. ACT-R supports, possibly nobody knows this, but a spontaneous retrieval. So if we add in a case where if the activation of a chunk is high enough, it'll lead directly to a retrieval of that if the retrieval buffer is clear. In Soar, we also have another kind of retrieval where if we know essentially if we know the symbol, the chunk name, we can immediately do a retrieval of that without bias by any metadata. We also update the activation of the selected chunk and the working memory chunk. So we're doing some more activation updates. So in terms of learning, that's really different between Soar and ACT-R. Whenever a buffer is cleared in ACT-R, we take the chunk and we copy it or move it into declarative memory. And in parallel with that, we're going to be updating the activation of that thing in work and declarative memory, because we might be actually putting back in something that's already there. And so we are updating that. Soar has a variety of learning and not learning mechanisms. So we actually have a direct storage mechanism, which we're unhappy about. And we also do updates to episodic memory. All right, so what are the commonalities among all these? So they all use these two systems. They use graph structures to represent declarative data, elements and chunks. They do procedural memory and declarative memory retrievals in this two-stage select and apply. Select searches long-term memory biased by metadata to find a single element. Once that element is found, we change working memory, we update metadata, and we do status information. That's what we do. That's what it's about. And we also have modules that interact through buffers in working memory. And with metadata, we have updates in parallel. The metadata is not readable or modifiable. And activation in all cases is seen to, numeric is used to focus attention on important memory elements. And learning is a side effect of procedural memory and declarative memory. Now you can say, yeah, there's lots of differences, and there's lots of differences, and these are the differences we know about. Fixed buffers versus unconstrained, single rules versus operators, retrieval is all or none from procedural memory versus Soar can fail in multiple ways that leads to impasses, and we have a single declarative versus a split. And we can focus on the differences, but I think I want to focus on the similarities. And for me, the question is, do we have a monster here? Is this a monstrosity? And I think no. I think there's this surprising observation that there's three types of information that drive these systems. There's agent data, there's agent metadata, and there's modular status data. And that's all that goes on in these systems. And what you're not seeing is you're not seeing that the architecture suddenly pokes something into working memory at certain points. You're not seeing that agent data can test metadata. This lives in one world as things are retrieved from procedural memory and declarative memory. This lives in another world where this is updated by the architecture as we're doing process of agent data. And this is updated when we do interactions between modules. I didn't expect to see this. Maybe this is obvious to everybody else, but this is, I think, a pretty strong statement. The future, finish the damn paper, analyze more architectures, figure out how to represent metacognitive and meta-memory appraisals, which seem to be different than what we've been talking about. These might be accessible to agent knowledge. So the fact that we have feelings of knowing, feelings of remembering versus knowing, all that status seems to maybe be something that pokes through and is available, some metadata that might be accessible to agent knowledge. Also want to incorporate more modality-specific representations, such as mental imagery, and we want to maybe fold this back into the common model at some point. That is it, except to say if you're interested about another way of looking at Soar versus ACT-R, my student Brian Stearns just finished his thesis, defended his thesis a week ago, and that involved re-implementing and extending Niels's PRIMS model in Soar. And so you can see someone who really took a Soar, tried to take an ACT-R model and figure out how to do it in Soar and what that led to changes in the modeling. So that's it. Thanks a lot for your attention. And I'm going to kick it back to Rob.